Hey guys, so it's Kenna here. We're going to go ahead and continue in our unit on electricity. Today we're going to be looking at electrostatics. Now you probably can figure out what that relates to just by kind of breaking the word apart. Electro, meaning electricity, and statics. Do you guys know what statics is? Static means unchanging or, stored in a specific form. So electrostatics is unchanging electrical charge. So let's go ahead and take a look at our essential questions for today and then jump right in. Number one, what is electron affinity and how does this relate to static electricity in the triboelectric series? Number two, what are the three ways of creating static charge and how do they differ? Number three, what is Coulombs Law and how is it calculated? Number four, what is lightning and what causes it? And number five, what is St. Elmo's Fire? Maybe one that you haven't heard before. I don't know. And how does that relate to electricity? Now, if you remember at the beginning of this term, we were talking about matter and thermodynamics, the structure of atoms, different kinds of molecules, these types of things. We've discussed that atoms are the building blocks of matter, and we should realize at this point now that material objects are made up of different types of atoms and combinations of atoms. The presence of these different atoms and different objects provides different objects with their own different electrical properties. One of these properties that we want to take a look at here is electron affinity. Now, in its simplest form, the property of electron affinity refers to the amount, for lack of a better word, of love or, you know, philia that a material has for electrons. If atoms of a material have a high electron affinity, then that material will have a relatively high love for electrons. So they like having electrons come to them. If they have a low electron affinity, that material is going to be unlikely to go ahead and attract electrons. And this relates to what we call static electricity. Now, the transfer of electrons from one object to another without further movement is known as static electricity. You may have done this in your living room with your sibling or cousins or something. You rub your socks back and forth on the carpet and you build up a little static electricity. Then you can go and shock them, right? Now, this static electricity is simply the buildup of electrical charges on an object. And there are three modes of creating static charge. You can charge by friction, by conduction, or by induction. And we will go ahead and explore each of these three in these notes. Let's go ahead and start by taking a look at charging by friction. Now let's suppose that a rubber balloon is rubbed up against your hair. During the rubbing process, the atoms of the rubber are forced into close proximity with the atoms of your hair. The electron clouds of the two types of atoms are then pressed together and are brought closer to the nuclei of the other atoms. The protons in the atoms of one material begin to interact with the electrons present of the other material. Amidst this kind of interaction, you hear a sound of crackling air. You might be able to even hear the atoms stake their claim on these electrons. The atoms of one material, in this case the atoms of the rubber, pull more on the electrons than your hair does. And as such, the atoms of the rubber begin to take the electrons from the atoms of your hair. And when the rubbing has stopped, the two objects have become charged. Your hair has become positively charged because it's lost electrons, which are negative, and the balloon has become negatively charged, which has gained electrons from your hair because they're negative. Now, if you really want to do this as a demo for yourself, the best thing you can do is to go ahead and make sure you maybe don't wash your hair for a day. Make sure that it's not wet. You want kind of dry and you want it easier to go ahead and strip those electrons away. But if you don't want to do it with your hair, you can do something similar by having, a little rubber rod and maybe some fur or something like that. Same sort of thing is going to happen. You're going to take the electrons off the fur and you're going to go ahead and bring them over to the rubber rod. Okay. So this is known as charging by friction. You're rubbing the two together and it causes the electrons off of one to move to the other. Let's go ahead and watch this video and we'll explain how it works.
Charging by friction. So when you're charging by friction, it's always between two neutral objects. So in this example, we're going to be looking at the ebonite rod and the rabbit fur. So the important thing to note is when you're looking at both of the images there, they're both neutral because they have the same number of protons as electrons. So if you're wondering which one will become negative and which one will become positive, what you need to do is you need to look at the electrostatic slash triboelectric series chart, and then that will help you determine which one will become positively charged and which one will become negatively charged. So when you actually do look at that chart, what you'll notice is the ebonite rod will be more likely to gain electrons, whereas the rabbit fur will be more likely to lose electrons. So your ebonite rod, since it gain electrons, it will become negatively charged after friction, and then your rabbit fur will become positively charged because it loses the electrons. So before rubbing, they're both neutral. While they're rubbing, the electrons will transfer from the fur to the ebonite rod. So after rubbing, the rod will be negatively charged and the fur will become positively charged, as you can see in the diagrams. So this is how you can get a charged object for use when demonstrating conduction or induction. And just the important thing to note is that these diagrams are crazy simplified. So there are obviously more than two protons, and there are still electrons present within the rabbit fur. It's just that the number of protons is greater than the number of electrons, making it positively charged. So just a reminder, there are three methods of charging within static electricity. There's charging by friction, where both objects are neutral, so they start out as neutral. And then the second one would be charging by conduction. So there's one object that's neutral and one that's charged. And then there's a scenario where they're both charged. And then the third one is charging by induction. So this is where there's one object that's neutral and one that's charged. And the key thing with induction is that there's actually no contact involved. So what I would suggest is if you need some clarifications on those other two types, charging by conduction and charging by induction, feel free to watch the other videos related to those specific types of charging.
Okay, so that's going to go over the basics, and it kind of introduced you to all three types. We'll go ahead and go over the other two videos here in a minute, but I wanted to go ahead and highlight the Triboelectric series that you talked about. Now, different materials, as we mentioned before, have different affinities for electrons. By rubbing a variety of materials against each other and testing their resulting interaction with objects of known charge, the tested materials can be ordered according to their affinity for electrons. Such an ordering of these substances is known as the triboelectric series and looks something like this. Okay. Now we can add more or less materials to this list based on their electron affinity, and that would make it easier for us to pick out which one's more likely to become positive and less likely to become positive. And they go on here because of their actual properties at the atomic level. Okay, you can see here that air is far more likely to become positive. Glass is up there, your human hands, wool, fur, these types of things. On the opposite end of the spectrum, you have a lot of your metals, nickel, silver, gold, but also things like wood, Teflon, and polyester. So materials on the right tend to have a greater affinity for electrons than those on the left. Subsequently, when any two materials on the table are rubbed together, the one that's farther right on the triboelectric series is more likely to go ahead and pull the electrons off the material that's on the left. Remember, just like in the video, it doesn't pull all of them, it just takes some of them, and this leaves the two materials charged. The ones on the right are more likely to be negatively charged. The ones on the left are more likely to be positively charged. Now, the next method is by charging through conduction. Now, if you remember when we talked about this with heat conduction, the two objects have to touch. Okay, so let's suppose a positively charged metal object is brought close to an uncharged metal object. If the two touch, the free electrons in the neutral one are attracted to the positively charged object, and some of those electrons are going to pass over. Since the second object, which was originally neutral, is now missing some of its negative electrons, it now has a net positive charge. and this is known as charging by conduction. Let's watch the video to go ahead and cover this.
Charging by conduction. There are two types of charging by conduction. One is between a neutral object and one that is either positive or negatively charged. The second type of charging by conduction would be between two charged objects. In this video, we're going to be looking at three different examples, and you can kind of see how they're color-coded to match the two different types of charging by conduction. So the three examples we're going to be looking at is number one, between a neutral pith ball and a negative ebonite rod. Number two, between a neutral electroscope and a positively charged glass rod. And number three, between a positive pith ball and a negatively charged ebonite rod. In our first example, we're looking at the neutral pith ball and the negatively charged ebonite rod. You can tell that the pith ball is neutral because it has an equal number of protons and electrons. You can tell that the ebonite rod is negative because it has a greater number of electrons. Now, if you're wondering how we got this negative ebonite rod, you need to refer back to the charging by friction video. So recall that charging by friction is when you're rubbing two neutral objects, and the object that's more likely to gain electrons will become negatively charged, and the item that is more likely to lose electrons will be the one that's positively charged, and that's all determined on the positioning on the electrostatic series chart. In this scenario, the negatively charged ebonite rod was charged via friction when it was rubbed with the rabbit fur. So the rabbit fur gave the electrons to the ebonite rod, making it negative. When we're dealing with conduction, it is charging by contact. So in this case, the rod will touch the pith ball. And when it does that, the neutral object, which is the pith ball, will take on the charge of the charged object. So the electrons will travel from the negative ebonite rod to the neutral pith ball. And so the pith ball becomes negative. In our second example, we're going to be looking at this neutral electroscope and the positive glass rod. And once again, conduction requires contact. So in this case, the rod will touch the sphere of the electroscope. And when it does, the electrons travel from the electroscope to the glass rod. Just a reminder, right? Your protons are not moving because your protons are with your neutrons within the nucleus. So the only thing that's going to be moving around will be your electrons. What you'll notice is the electrons at the bottom, right, kind of like where the foil leaves are, they move up due to the attractive forces because negative and positive charges they attract, right? So the negative electrons from the foil leaves are being attracted to the positive charges that are on the glass rod. Okay, just a reminder again, your protons, they don't move, they stay in the same spot. It's just your electrons that are moving. In this case, the glass rod then becomes less positively charged and the electroscope becomes positive. And what happens is that the leaves at the bottom of the electroscope, they repel due to the law, right? Like charges repel. So if both of the leaves there have predominantly positive charges, they're both the same charge, right? Like charges. And so they'll repel, which is why their leaves will spread apart. This third example of charging by conduction is between two charged objects. So we're going to be looking at the positive pith ball and a negatively charged ebonite rod. The pith ball is positive because it has a greater number of protons and electrons, and the ebonite rod is negative because it has a greater number of electrons compared to protons. The pith ball was positively charged by touching a positively charged glass rod through conduction, whereas the negative ebonite rod was charged via friction by rubbing with the rabbit fur. Conduction requires contact, so the pith ball and the rod will touch. And if you recall the law of attraction, opposites attract. Positive charges and negative charges attract each other. So in this case, the positive pith ball will be attracted to the negative ebonite rod. And what happens is the two objects will then try to distribute the electrons as evenly as possible. So in this case, the electrons will travel from the negative ebonite rod to the positive pith ball, and this will occur until the charges are distributed as evenly as possible. And what you're going to be left with are two objects that are neutral that no longer have an attraction with each other. And just a reminder, there are three types of charging within static electricity: charging by friction, charging by conduction, and charging by induction.
Okay, so again, I want to highlight, she already did, but that protons do not move. Remember, they are attached inside the nucleus, and those forces that are holding it to the nucleus are not going to let that go. So it's only the electrons that are in the outer cloud that are actually able to move between the different objects. So let's go ahead and finish up looking at how we can get static electricity by taking a look at charging by induction. In this particular instance, you have a positively charged object brought close to a neutral metal rod, but it does not touch it. That's a big thing. Conduction is by touching. This will not touch. And although the free electrons of the metal rod do not leave the rod, they still move within the metal towards the external positive charge. And this leaves a positive charge on the opposite end of the rod. So you're building up charge in different places that we're going to go ahead and take a look at. So that leaving the positive charge on the opposite end of the rod. So because they're not touching, you're not losing any of the electrons. They're simply moving to a different part of the object, which causes two kind of pools, if you will, of charge on different parts of the object. No net charge has been created in the rod. The charges have simply been separated. This process is known as charging by induction. Let's go ahead and watch the video here.
Charging by induction. Charging by induction is between a neutral object and a positive or negatively charged object. In this example, we're going to be looking at the neutral wall and a negatively charged balloon. You can tell that the wall is neutral because it has an equal number of protons and electrons. You can tell that the balloon is negatively charged because it has a greater number of electrons. Now, if you're wondering how did we get this negatively charged balloon, you need to refer back to the charging by friction video, right? So charging by friction is when you're rubbing two neutral objects. The object that's more likely to lose electrons will be positive, and the object that is more likely to gain electrons will be negative, and it's all determined by their position on the electrostatic series chart. So in this case, the rubber balloon is the object that gained the electrons. So that's how we get this negatively charged balloon when we are charging by induction. So in this case, with charging by induction, there is no touching. So this balloon is going to be brought close to the wall, but it's not going to touch the wall, and yet it's still going to induce a charge. If you recall the law of attraction, right? Like charges repel and opposites attract. So in this case, the electrons within the balloon, right, repels against the electrons that are in the wall because the two negative charges, they repel each other. So the electrons are going to be shifting back, and that shifting back is called induced charge separation. What you then get is a positive charge on the wall surface, right? So the balloon, right, the negatively charged balloon induces a positive charge on the wall surface without even touching the wall. But just a key thing to remember is that when the balloon is moved away from the wall, then those electrons are going to move back forward. So then that charge will go away. And that's induction. So just a reminder, there are the three types of charging within static electricity: charging by friction, charging by conduction, and charging by induction.
Okay, so now we've gone over all three forms of charging to produce static electricity. The other thing we want to understand about this is that when we put an object into a field, and I know we haven't talked about fields just yet, but when you put it into proximity to another particle, those forces of either attraction or repulsion can actually be calculated. And the way we go ahead and calculate the force between two charged particles is using Coulombs law. Now, we've seen that this force exists, and we even talked about an attractive force between two opposite charges, or a repulsive force that exists between two of the same charge. So What impacts the magnitude of this force? Well, the French physicist Charles Coulomb was able to determine that the electric force on one object from one object onto a second object is directly proportional to the charge that they have and the distance between the two of them. And he came up with what's known as Coulombs Law. So in Coulomb's law, if the charge on either one of the objects is doubled, the force doubles. He also discovered that if the distance was increased between the two objects, the force decreases with the square of the distance. So this is another inverse square law, which is very similar to what we saw when we were looking at Newtonian gravitation. Okay. In fact, if you take a look at the equation down there in the lower left-hand corner, it looks very similar to the one that we had for Newtonian gravitation. Okay. Instead of K, we had the capital G as the gravitational constant, and instead of Q1 and Q2, which are charges, we have M1 and M2, which are masses. All right. Because we're using charge instead of going ahead and using masses, this means the gravitational constant is not going to be the same as what we saw with the Coulomb's law electric constant or Coulomb's constant. In this case, we're going to be Newton meters squared per Coulomb squared. So coulombs, remember, is our unit that we use to go ahead and measure charge. Okay, and we need that to go ahead and cancel out if we're going to go ahead and get force in newtons. And so this unit makes sense just like the one for the gravitational constant in Newtonian gravitation. All right, so two balloons are charged with an identical quantity and type of charge, minus 0.0025 Coulomb. They are held apart at a separation distance of 8 meters. Determine the magnitude of the electrical force of repulsion between the two of them. Now, how do we know that it's repulsion? Well, if they're the same charge, remember the same charge means that we're going to go ahead and have a repulsive force. If they were opposite charges, we would then have an attractive force. And we're just going to have to remember that in terms of the definition. Now let's go back really quickly and take a look at this equation. F, or the force created by the electrical attraction or repulsion, is equal to K, which is Coulomb's constant. And this is going to be times Q1, the charge of the first one, times Q2, which is the charge of the second one. And that's going to be divided by the distance squared. So as we go ahead and do this on the next page, I want you to follow through and go ahead and practice this problem. And then we'll go ahead and see if you can get the answer on this. All right. So that's 9. You might want to write this down. 9 times 10 to the ninth Newton meters squared per coulombs squared. And that's Coulomb's constant. All right. So pause the video here and go ahead and do the math. And then we'll see how you did on it. All right. So let's see what you got. As we go ahead and go through this, we need to go ahead and start. I'm going to go ahead and use, well, let's say yellow today. And so the gravitational force, or in this case, the electric force, F, and I'll put F for E, force electric, is K, Q1, Q2 over D squared. Oops, squared. Okay. And this equals 9 times 10 to the ninth Newton meters squared per coulombs squared. That's going to be times the charge, which we have right up here, minus 0.0025 coulombs. And since they're both the same, I'm just going to go ahead and square it. And that's going to divide it by the distance. And in this case, we have distance is 8 meters. And that's going to also be squared. Okay. When we go ahead and do the math, 8 times 8 is 64 square meters. And up here, we're looking at, well, I'll just write it in scientific, 6.25 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the negative 6th coulombs squared. All right. Now remember that this is going to be times the constant over here of K. So coulombs squared is going to cancel. Meters squared is going to cancel, which leaves us with a unit of newtons. So that's 6.25 times 10 to the negative 6, and we'll times that by 9 times 10 to the ninth. And the answer we get is, wait a minute, 64. Yeah, is 56,250 newtons divided by 64. So we divide by 64, and that gives us force electric is equal to 870, that's an 8, 878.9 newtons. Now, notice that because we're timesing a negative times a negative, it becomes a positive, okay? But if we did a negative times a positive, this would be a negative. And so what does that mean in terms of our frame of reference? So the negative in this case is going to be an attractive force, and the positive is going to be a repulsive force. And we can go ahead and double check and see if this matches my math from last night. Okay. And 878.9 newtons. Very good. Okay, so that's how you go ahead and use Coulomb's law. It's pretty straightforward as long as you know where to put everything. We just want to make sure that we understand what all those pieces mean and why the units come out the way that they do. Now, most of you have probably done this where you go ahead and do the static electric buildup by friction using your socks in the carpet, and then maybe you touched a door handle or you touched your little brother. As you walk across the carpeted floor, your body is starting to build up that static charge. When you reach for a metal doorknob, the charge flows between your hand and the doorknob and you feel a shock. This is what's known as a static electric discharge. But this isn't the only place that you can see a good example of this. We also have static electric discharge in lightning. Okay, so the clouds are going to go ahead and rub against each other and run up against the air, and they're going to build up pockets of positive and negative. And what happens is when you see lightning, it's doing that discharge. It's trying to neutralize those pockets of charge because, as you've learned in most of your classes, objects like to stay neutral. They don't like to be charged. Ions don't prefer to stay charged, so they create ionic bonds. In this case, we don't like having built up static electricity, so it's looking for a pathway to discharge that built up charge. So this is showing you exactly that. You can see at the top you have a positive charge built up on the one cloud and negative built on the other. You can actually get lightning between clouds as it tries to neutralize this. Or you can get a buildup of charge on the ground, and then they go ahead and start bridging the gap between the clouds and the ground, which is what we would consider to be a lightning strike. Now, I gotta warn you, I thought I'd show you some cool lightning strikes, and these are definitely some pretty amazing lightning strikes. The guy is a little interesting, but he does make it kind of fun. So enjoy this video looking at his top 10 lightning strikes. Some of them are very, very impressive.
Lightning can manifest itself in many dramatic and beautiful ways, from spectacular anvil crawlers to extremely powerful bolts that leap miles away from the storm. I've been chasing lightning for 20 years, and here are my top 10 best lightning strike captures. Number 10 was caught this year on a Kansas interstate. Looking back in slow-mo, you can see the distant discharge triggering the closer strike. I'd wager this trucker probably got brown all over his pants after spilling his coffee. Number 9 was bagged under a tornadic supercell near Lincoln, Nebraska. Lightning was crashing all over the place, but what makes this bolt so striking was its bizarre looping path. Number 8 occurred on May 31st, 2013 near El Reno, Oklahoma. This historic and horrifying day saw the birth of the world's largest tornado at 2.6 miles wide.
Jesus.
And the fact that there's a bolt of fire shooting out of its massive infant side makes this strike worthy of this list. You don't have to be close to the strike to get a great shot. In fact, many of my favorites have been captured from miles away. In these snags, it's another beautiful element like a rainbow or the wild colors of a desert sunset that make them extra spectacular. Number 7 was summoned over Devil's Tower. It took me 300 tries before this storm finally served up the wicked goods. Anvil crawler lightning, also called spider lightning due to the way it scampers across the sky, is one of nature's most dramatic displays. I've photographed hundreds of anvil crawler webs, but only once lurking over an old paralyzed 1956 Mercury. That's why this snag is number 6 on the list. Number 5, 4, and 3 all come from one intense evening. In June of 2010, a violent storm in North Texas was bombarding the earth with constant bolts of positive lightning. When the strikes are slowed down, you can really see individual flashes that make lightning flicker. It's this super long megabolt and its 14 separate flashes that scores number 5 on my favorites. Positive lightning is the most deadly of the bolts. They leap from the tops of thunderstorms out to the ground up to 10 miles away.
Wow.
To complete this stealthy journey, they can generate 1 billion volts. Plus, when these daddies fire, they can heat the air to over 50,000 degrees Fahrenheit. That's over 5 times hotter than the surface of the sun. Because of their tendency to leap away from rain into low storm clouds, they're extra photogenic, and on this day there was so much positive lightning crashing all over the place that my chances of getting that super close high-res photo I've always dreamed of was within grasp.
Hey, come on, seriously.
As were my chances of becoming another charred toad on the side of the road. Either way, something inevitable was about to occur. 2 positive flash discharges, forking to the ground in 4 locations, and then a 1 in a million shot of a bolt crashing into Earth with a rare, clear capture of something called an upward streamer sparking up from the ground. Lightning is not concerned about striking in your frame, or being photographed at all, but every now and then she feels down to earth, turns to the camera, and strikes a killer pose. Here's number 2 again. Alright, let's get to number 1. June 16th, 2014 in northeast Nebraska. 2 tornadoes are on the ground. The skinny one on the left is blazing a trail towards its chubby sister on the right. And as if this wasn't already epic enough.
Oh. Did I just see that?
And one more time. Blows my mind every time I see that. Well guys, thanks for watching and liking my videos. If you have any questions about lighting or photography, shoot them on over in the comments. If you're gonna go out chasing lightning, remember that if you can hear lightning, you're close enough to be struck. So always carry a good set of earplugs with you. Till next time.
Okay, so he's a little funny, but I'm not encouraging his type of dialogue, but some pretty amazing shots of lightning there. Okay. The last thing I wanted to finish with today is St. Elmo's Fire. Now, St. Elmo's Fire is a weather phenomenon involving a gap in electrical charge. It's like lightning, but not quite. Originally, it was mostly seen by sailors high on the seas during a lightning storm, because St. Elmo's Fire is actually a form of plasma. It's simply sparking caused from the tearing apart of molecules like you would see in a neon light. It's the combination of gases in the atmosphere that make it seem blue rather than orange of neon. And as you can see kind of in this old ship's drawing here, it typically seemed to glow off the upper pieces at the edge of the masts. Okay, so you can see that there's kind of these little spark coming off those edges. And this is what you see today. Most of the St. Elmo's Fire that people see is actually seen in airplanes. the nose cone in particular of airplanes as they go through particular types of electrical storms can actually produce some St. Elmo's fire. So I have a quick little one that's going to go ahead and show you this, and then we'll go ahead and finish up with an explanation of how it works. So this is St. Elmo's fire. These are these little dots on the nose cone of the aircraft. Notice the very blue color of it. This is from a pilot who's flying in the jump seat. So you get the idea. All right, so that's all I've really got for you today. I'm going to show you this one last video where he explains how St. Elmo's fire was formed, and then we'll call it good.
This week's word is St. Elmo's fire. No! And ladies, before you even ask, Rob Lowe was not available to guest host this week's weather word. You guys put his face on my head, didn't you? I'm Storm Team Meteorologist Jason Myers, and St. Elmo's fire is a very rare weather phenomena consisting of a bright blue or violet glow with an often audible electric discharge emanating from a single point like a lightning rod, an aircraft antenna, or even a ship's mast. When an electric field around an object reaches a value of about 100,000 volts per meter, it causes air molecules to ionize and turn to plasma. This produces a faint glow visible in low light conditions. It's kind of like nature's neon light. The only time you'll see this naturally occurring is during a thunderstorm when there are high voltage differentials between the clouds and the ground, and they're most often seen by pilots when flying through a storm. Have you ever seen St. Elmo's fire, the phenomena, or the movie? Let me know in the comments below, hit me up on Twitter, or send me a message on the Storm Shield Facebook page. As always, thank you for watching. Please like the video, subscribe to the channel. I'll see you in a week.
All right, guys, that's all I've got for you. Stay safe, stay healthy, and I'll talk to you soon. Take care of yourselves. Bye-bye.